I'm really excited to tell you guys today about Rendezvous. This is some new work we're doing in the area of metadata hiding communication. And this is actually, you're the very first audience to ever hear about this work. It has not been spoken about anywhere else. And it's so new that actually the paper and the code are not online either. So this is like, you heard it here first. We hope to have the paper online along with the code sometime in the next month. We're just kind of putting the finishing touches on it now. And this is joint work with Henry Corrigan-Gibbs and Professors Matei Zaharia and my advisor, Dan Bonnet. So, yeah, so the story with this talk, like many stories, begins with injustice. So it's not very important what the injustice is. It's just, it could be that there's some government that's oppressing some population. It could be that there is a corporation that's secretly having a lot of corrupt practices. But what is important is that somebody sees this injustice and they decide, I need to tell somebody this has to change. So they go and they seek out a journalist, they seek out someone who works for a news organization that can kind of tell this to the world without worrying about reprisal. So maybe they go to a conference, maybe they track someone down in a coffee shop, and they have kind of a secretive communication. But then they leave and they need to stay in touch. They need to send supporting documents to the journalist. They need to send more information. And they have to have some way to communicate, because they can't always come back to this conference on a weekly basis or something. So what are they going to do? And today, their best bet is probably to use some sort of end-to-end encrypted messaging app like Signal or WhatsApp. And these are great because they hide the content of your messages, not only from other people, but from the service providers themselves. So if they get subpoenaed or hacked, they won't be able to give up your messages. But the problem is that this is really not quite enough if you're dealing with something very sensitive. So for example, if you're working for some company and the New York Times does this big expose on corrupt practices at your company, then if somebody at your company finds out you're talking to some journalist at the New York Times, they don't need to know what you told that journalist. They already read it on the front page of the Times. What's important is the fact that you were talking in the first place. Moving from companies to government, there was a kind of a now famous quote from a US general and former director of the NSA that says, we kill people based on metadata. So if you are working with data that's somehow very, very sensitive, you need to be concerned not only about the content of your messages, but also with the metadata of who you're talking to. So if you want to go kind of one step further than these apps, you can use anonymizing proxies like Tor or SecureDrop, and these are systems that are actually used by news organizations today to communicate privately with their sources, and they try to hide this kind of metadata. But the problem is if you're up against a global adversary who can kind of look at traffic on the network, something like a nation-state actor, then you're still in trouble because they're able to break the security guarantees that these services provide. So this gap in what's available versus what's needed has motivated a ton of research in metadata hiding communication systems. So here's a list of a few that you might have. I think I'm running out of batteries. Here's a list of a few that you might have seen. It's kind of a very, very long list. And people have built systems for kind of any kind of communication task you could imagine. So the classic two-way messaging is there. People have thought about group messaging. People have thought about anonymous broadcasts where you just want to send the message to everyone, like Twitter. There have been systems for like microblogging where people will anonymously post things and you can subscribe to their streams. So there's kind of anything you can imagine. Someone has thought about it. There's a lot of different approaches. But if you look at this list of approaches, there's this one kind of surprising and glaring limitation that is always there, and that it's like they always seem to require somehow running in rounds. So these systems will always split up time into discrete time epochs, and then you'll send a message kind of in one epoch, and then you'll get the message someone sent you kind of in the next time block. And everything will either run strictly in rounds, or will have some loose requirement that you need to regularly be online and connecting to the server in order to get the security guarantees that you want. And so this got us thinking, like, is this something that's intrinsically required? Is there something about metadata hiding that requires everyone to always be online and kind of walking in lockstep? Or is there some way to get around this? Is there some way to get metadata hiding without relying on rounds? So the answer to this question is our new work, Rendezvous. And Rendezvous is the first metadata hiding communication system that has no requirements for users to contact servers at regular fixed intervals. And so the functionality that Rendezvous provides is that journalists are able to register mailboxes on the system, and then users and sources are able to come to the system and write messages into those mailboxes without worrying about the metadata being leaked. And I'll be more precise about what we mean for the security in a second. So in addition to this kind of qualitative improvement that we don't require rounds. We make some technical contributions to how the metadata hiding system works. So asymptotically, we improve client computation costs to being logarithmic in the number of registered mailboxes. We reduce communication costs to being logarithmic in the number of mailboxes. And this is all improving from prior work where it was square root. And practically, this translates into 4 times improvements in server-side processing costs, 8x improvements in the client-side costs, and 1 or more order of magnitude reduction in the amount of data that the parties need to send back and forth. So the way that Rendezvous works is it's a 3-server system, and we want to provide security against arbitrarily many corrupt users. So users can do whatever they want. They can send corrupt messages. They can deviate from the protocol I'm going to describe, anything. And they're also even allowed to compromise one of the servers. So if one of the servers gets subpoenaed, if one of the servers gets hacked by the malicious users, we want to be secure in that case too. The functionality we're going to support is that someone can go to the servers and register a mailbox. Anybody can then go and privately write into the mailbox that they've been told about, and they can do that without leaking which mailbox they're writing to. And then the owner of the mailbox can check whenever it wants to see if it's received messages. In terms of what the servers are going to be doing, there's two servers, A and B, are going to be doing the bulk of the work. So they're going to be handling the read and the write requests. They're going to be maintaining the databases of mailboxes and all the data. And then this third server, the auditor, is going to, every time someone tries to write something into the system, is going to receive a little bit of information from each party, and it's kind of going to look at this information and blindly filter out any malicious requests. So this is our system for defending against someone who's trying to corrupt the databases by sending some kind of malformed request. And I'll talk a little bit more about how we do that in a minute. In terms of security, there's kind of some more nuance to what kinds of security guarantees we provide, and we're able to do different things in different settings. But for the purposes of this talk, the main guarantee we want is that when someone sends a message, you want to be unable to tell who the recipient of that message is unless you are the recipient of the message. So if you're the recipient of the message, you know you got the message. And if you're anybody else, including if you're one of the servers, you shouldn't be able to know who that person who connected to you was actually sending mail to. So for the rest of this talk, I'm going to start by talking about how we're able to do this metadata hiding without rounds. And first, I'll describe it in the setting where everybody plays by the rules and honestly follows the protocol. And then I'll describe our system for handling malicious parties and how we kind of extend our protocol to handle parties who can cheat in arbitrary ways that maybe we haven't even thought of yet. And then I'll give you a little bit of information about how we've evaluated the system and our practical performance improvements. So the main tool that's going to help us do this private writing is something called the distributed point function. And this is an idea that was invented maybe 5 years ago. And it has, it's kind of a neat crypto trick. So I'll tell you about that first. You might recall from high school what a point function is. So a point function is a function f where if you evaluate at any point, the function is 0. Except for at one point, it'll be something that you specify. So here is a function that if you evaluate it at 0, 1, 2, 4, it'll always be 0. But if you evaluate it at 3, you get the string high. Now, what a distributed point function is it's a trick where you can take a function that's a point function and split it up into 2 other functions, and these are not going to be point functions, such that if you XOR the evaluations of those functions at some point together, you're going to get back the output of the original function. So if you see here on the slide, we get f1 and f2 out of our distributed point function. And if you evaluate them at some point, you're going to get things that look kind of random. So you can't really tell what the original point function was. But then if you take the output of the 2 things at the same point and you XOR them together, you're going to get back what the output of the original point function was if you had the original point function. So that's what a distributed point function is. It's kind of a neat math trick. We don't need to go into the details of how it works. But what's interesting is that we're actually able to use this for privately writing into a database. So the way that works is if you have someone who comes along and says, hey, I want to write the message hi into address number 3, they start out by generating the point function that we saw on the previous slide. And then they send, then they run this distributed point function and they get back the 2 functions f1 and f2. And then they send off those functions to the 2 databases, to the 2 servers that are holding the databases of mailboxes. And the nice thing about DPFs is that this representation of these functions f1 and f2 is not this big table that I just showed you on the slide. It's somehow a compressed representation, so it doesn't take up a lot of space. But this isn't kind of our new work, so I'm not going to go into the details of how that piece works. So once the servers have the DPFs, they evaluate them at each mailbox address. And as a result, now the servers have the contents of the functions f1 and f2 in their mailboxes. So if someone comes along and now wants to read from some mailbox, like if I want to read from mailbox 3, I can read from each of those 2 mailboxes, and when I XOR what they had together, I get back the message hi. So even though each of the 2 servers doesn't have the message, when you contact them both, you can get back the message that you wanted to read. Now, if some second person comes along and wants to write another message, maybe to address number 1, they would also have a DPF. They would have that DPF's contents written to both databases. And because the contents of this first DPF XOR to 0 at all the other points, when this new DPF is put into the database, the contents of the previous message will kind of XOR out to 0 if they write to mailbox 1, and then that person's message will be readable. So in this way, you can kind of do a lot of private writes into the database in such a way that you can't tell who wrote where. So that's the trick with distributed point functions. But the question is now that we've done this, it's kind of a lot of work, it's a complicated system, have we hidden metadata? And the answer is no, we have not hidden metadata. In fact, we haven't even hidden regular data, because as I described it right now, anybody can contact the servers and read what's at any mailbox and just read everybody's secrets sent to everybody else. So we need some kind of defense against that. So for hiding the regular data, the encryption does a good job. So first, we encrypt each row by the owner of the mailbox. So if the New York Times wants to register a mailbox, they register the mailbox and they encrypt the contents of that mailbox with their key. The Washington Post does the same thing for their mailbox, and so on. The only important nuance here is that you can't actually use the same key on both servers. Each server needs to have their databases encrypted with a separate key. And the reason for this is we want it to be resilient against attackers who are actually able to compromise one of the servers. So we don't want it to be the case that if you can compromise one server, then suddenly all the keys are lost. So it's important that the 2 different servers have 2 different keys for each mailbox, so that you can compromise one and still not be able to access the contents of someone's mailbox. So encryption is easy, but then there's the question of metadata. And we still haven't covered metadata either, and that's because what I've described so far is susceptible to what we call a polling attack. So what this attack is you read the contents of each mailbox, and you can't tell what's in the mailboxes because they're all encrypted, but you get some encrypted blob. And then somebody writes into the database and writes something to someone's mailbox. And because of this hiding stuff, maybe you can't see directly who was written to. But now you go and you read every single mailbox a second time. And you notice that because of the distributed point function, zeros have been written into every mailbox, except for one mailbox where there's been a message written. And you still don't know what message was because it's encrypted. But because something has changed, now you know where the writing happened. So you need some way around this. So we have a trick where the servers non-interactively re-randomize the contents of their mailboxes while they're doing the DPF evaluation. So while they're doing the writing into the mailbox, they also re-randomize at every step. And this is very fast, and the cost is very low on top of the original evaluation of the DPFs. I unfortunately won't have time to talk more about this, but when the paper is out, you can read about all the details if you like. But there's kind of a more fundamental problem. So I've described how whenever somebody connects to the system, you don't know which mailbox they've written to. But if we've built a system that's for journalists and for sources, and the only people who connect to this system are either journalists or whistleblowers, you have a problem because just the fact that someone has connected is actually revealing that they have some secret that they're somehow incriminates them. So we need some way of having plausible deniability for someone who connects to the system. And there's a really neat idea about how to do this from a few years ago. And this idea is that cooperative websites who want to be kind of a good team player can embed some JavaScript into their web pages that whenever someone goes to that page, your browser generates a request and sends it out to the system. So that when somebody contacts the system, you don't know, were they actually leaking something? Or did they just happen to go to a website that then, without them doing anything, sent a request into the system? And there are actually a host of kind of security and also ethical questions about doing this. And we do discuss these in our paper. I'm happy to talk about them later if you're interested. But the new idea here is that our design of Rendezvous is actually really, really well aligned with using this approach. And there's 3 reasons for this. One is that the incentives are aligned really well. So news organizations have websites that get tons and tons of visitors from all walks of life. And news organizations are also the ones who stand to benefit from using this system. So the incentives are aligned for news organizations to be the ones who put this kind of stuff into their web pages. And because they get so many users, like not everybody who reads the New York Times is leaking information to the New York Times. So there's some plausible deniability there. Another nice thing about our system is because our costs are our metadata hiding property means that when somebody writes into the system, it hides who's being sent a message. The outcome of this is that if you want to have lots and lots of people sending dummy messages to a web page, all you need to do on the server side is to create one new mailbox, and that will be kind of the dummy recipient mailbox, and everybody will send their mail to the same mailbox. But because of the metadata hiding guarantee, nobody will know where those messages went. So you can get kind of good metadata hiding with great plausible deniability without having to increase the message processing cost on the server side by more than a tiny bit. That's the cost of one new mailbox. And the last thing is that, and you'll see this more when I talk about the evaluation, but the client-side costs in Rendezvous are very low. So if you embed JavaScript on a web page, your concern is this going to slow down the web? Is this going to damage the user's experience? But you'll see that both in terms of computation cost and communication cost, they're very, very low. So that even if someone is in a resource-constrained environment like a mobile device where data might be costly, this won't really be a problem. So this is kind of the high-level view of how we provide metadata hiding and how we give plausible deniability. But maybe the more challenging question is how do we handle users who want to disrupt the system? Naturally, a system that tries to provide this kind of security will have a lot of people who are unhappy about it existing and will want to take it down. So we need to be able to provide security against any number of malicious users. So if everybody trying to connect to the system is actually trying to take it down, we need to be able to be resilient to that. And we also want to be able to be resilient to servers being taken down as well, or servers being compromised. We have to make the one caveat that the servers are trusted for availability. So what I mean by this is one trivial denial of service attack is to unplug one of the servers, and then the system doesn't work. So there needs to be some sort of robustness from a system side. But we're interested in robustness in terms of security. So we're interested in if a server deviates from the protocol, still services requests, but tries to do something that will leak users' information and kind of learn something about who is writing messages to who. So there's two kinds of attacks that I'm going to talk about. And the first one is if a disruptive user is trying to write to somebody else's mailbox. So we use encryption to make sure that if you're trying to read from somebody else's mailbox, you won't be able to. But I've said nothing about what if you want to write to somebody else's mailbox. And the problem with this is if I want to do a denial of service attack, all I need to do is just write bogus messages into everybody's mailboxes. And so my message gets XORed into every mailbox. And then when real people go to write, the reader won't see the actual message. They'll just see some random garbled junk that I put into their mailbox. So our solution for this actually borrows a page from kind of classical operating systems approaches and uses it in a new way. And the idea here is virtual addressing. So if our problem is disruptive writes to other people's mailboxes, one solution is to blow up the address space of mailboxes to something that's kind of exponentially large. And if you have an exponentially large address space, unless you've spoken to a journalist and been told, hey, this is the address that you should write to, if you're trying to guess at random about where people hide their mailboxes, you're very, very unlikely to hit a real mailbox because they're spread out very sparsely in this gigantic space. The problem here is if you have a huge number of addresses on the server side, you have to evaluate a DPF at a huge number of addresses, and this is infeasible to do computationally. So this is where virtual addressing comes in. So in our final system, the clients will send in their requests to the servers as if they're trying to write into some exponentially large database, and they know the kind of the address that they want to write to. But on the server side, there's an address translation table so that the servers don't need to compute the DPF at every possible address. They only need to compute the DPF at the virtual addresses that correspond to physical mailboxes that have actually been registered with them. So that's how we're going to deal with people trying to write into other people's databases, into other people's mailboxes. But there's kind of a second and much more sinister problem. And that is that I've been talking about DPFs and people forming these functions and splitting them in half nicely. But what if someone just decides to deviate from the protocol completely? And instead of sending these two functions, F1 and F2, that nicely XOR into a point function, why don't they just send some garbage to the two servers? The servers will think they're working with a DPF. They'll write something into every mailbox. And then when someone goes to read, there will be trash written to every mailbox. And this would be an attack that really requires no sophistication. You just send random junk to both servers, and all the mailboxes get stuff written to them. And yeah, this kind of disrupts the whole service without having to know any mailbox addresses. So the solution for this is to have the third server. So far I've only been talking about a 2-server system, and our thing is a 3-server system. The role of the third server is just to be this auditor. So whenever someone tries to write something into the database, everybody sends a short message to the auditor, And the auditor can kind of blindly, by looking at these short messages, learn nothing about who's writing to who or what messages are being sent, but it can detect if the write that was going to go into the database is actually corresponding to a DPF, or if it's just some malicious junk. And it's able to detect that, and then we can filter it out. So that's what our auditing is. And in our system, we have a new auditing protocol that is logarithmic in the number of mailboxes in both computation and communication costs. And this is compared to prior work where all of these costs were square root. Unfortunately, there isn't enough time for me to go into the details of how the auditing works. I even had slides on it, but it's just there isn't enough time in half an hour. So if you want to talk about it afterwards, I'm really happy to talk about it. I think it's very cool, but there won't be time to talk about it now. But I do want to tell you about how it performs in terms of evaluation. So when we run the auditor, we compared it to Riposte, which is a prior system from our group a few years ago. And Riposte also has this kind of auditing approach. And you can see here on the graphs on a log scale that in the client and auditor sides, computation is very, very cheap. In fact, even when you go up to 1 million mailboxes, the auditing computational cost is like less than 10 microseconds. So it's pretty much for free, the auditing on the client and the auditor. And on the server side, there is a little bit of an increase. But on the server, the auditing is actually not the bottleneck. The bottleneck is doing the computation on these DPFs. So it's not a big problem to add a little bit to the auditing cost because we're saving a lot on the client and the auditor. And as a result of this, because the auditing has gone from kind of expensive to almost for free, now we get an 8 times improvement on the client-side costs, because most of the client-side costs previously was preparing, or at least if we use the previous auditing system, most of the client-side costs would be preparing these messages for the auditing and not the actual preparation of the messages to write. So when we look at the client-side costs, like I said, it's asymptotically logarithmic in the number of mailboxes. But in practice, because this logarithmic component is just due to the auditing, which takes less than 10 microseconds and is practically for free, if we go from 100 mailboxes all the way up to 1 million mailboxes on the server side, we get almost no increase in the actual computational cost. So although asymptotically it's logarithmic, practically it appears to be kind of constant, which is really great. And because we were interested in this kind of a web dummy messages approach, we re-implemented our system. The original system was written in C and Go. We also re-implemented it in JavaScript to generate the client messages there and measure that. And in JavaScript, it's still taking less than 60 milliseconds to generate and send a request. So this is very, very fast. Another concern if you're deploying these things on the web is, well, is adding this going to increase communication costs? So we looked at how big our scripts are. And the JavaScript component, as well as all the dependent libraries, come out to about 70 kilobytes. And I looked at the websites for the New York Times, Washington Post, and Wall Street Journal, and it comes out to about less than 2% of the size of these websites in terms of the amount of data on the browser. So it's not a big additional cost in terms of download. Another question is maybe downloading the script isn't big, but maybe it's causing your device to do a lot of communication and costing you a lot of data. So we looked at our communication costs, and we compared communication costs to Riposte and another system, Pung, that does kind of two-way messaging. And if we look at about 16,000 mailboxes, we get a 10x improvement in communication costs. If we move up to about 1 million mailboxes, we see that on the client and the server side, we're getting 100 times reduction in communication costs. And in terms of auditor, we're getting a 50 times improvement in communication costs. So we're getting 1 or 2 orders of magnitude improvement in terms of communication cost. So that's all I wanted to say about Rendezvous. So it's the first metadata hiding communication system that has no synchronization requirement between the servers and the clients. And asymptotically, it speeds up a lot of protocols from square root in the number of mailboxes to logarithmic. And this translates into practical improvements of 4x on the server side and 8x on the client side, and 1 or more orders of magnitude reduction in communication costs. So if you want to talk more about this, I'll be around at lunch. You can email me, and the paper and the code should be posted pretty soon. So keep your eyes peeled for that. Thanks. Careful. Yeah.
Wonderful talk, Saba. This might be part of the stuff you skipped, but if the auditor is only getting information from the DPF that's encrypted using different keys that the auditor evidently doesn't have, how can it possibly tell if it's a valid DPF?
Yeah. I'll show you. I had all of these great slides about the problem and how it turns out that it's an instance of a more general problem, and then you can do this thing where you recursively prove that you're not writing to one half of the database, and then you can cut the database in half and do this, and it's logarithmic. So it's kind of a very neat new crypto protocol. It's not enough time to talk about the details. Happy to talk about it offline. Yeah.
I wanted to make sure she got her 10,000 steps in. So if the data, if you have the keys, why wouldn't the distributed point function be not zero everywhere on the encrypted data and only match it on the decrypted data?
So the way that we're doing the encryption is you encrypt something with a pseudorandom function, and then you XOR it into the database. So it's kind of a mask. So you can still XOR stuff into the database and out of the database, and it'll change the underlying.
But since the anonymity comes from the fact that there's one that it's a point function, right?
Right.
Could you obscure that by doing the encryption so that you wouldn't know which one evaluated to a non-zero unless you had the decryption key for that one slot?
Right, so this is exactly what we do. The distributed point function, you don't know where it's writing zeros and where it's writing non-zeros, but you know that it has this guarantee that it writes a non-zero value to one place.